This is the second video on section 2.1 vectors. And in this video we're going to look at vector arithmetic, and in particular addition and subtraction. Now, something that I say very often in my classes is there are things in mathematics that work the way you want them to, and there are things in mathematics that does not work the way you want them to. One of the things that does work probably the way you want it to is vector arithmetic. So, definition 19 and 20, vector addition and vector subtraction. And the definition works the way you want it to work. So you want to add two vectors together. A vector plus a second vector is a third vector. And you get the third vector simply by adding the components. The vector v minus the vector w is another vector called v minus w. And you get that vector simply by subtracting the components of w from the components of v. So, example 21, v is our vector -1, 3, w is our vector 2, 7. What is v plus w? It's the vector 1, 10. -1 plus 2 is 1, 3 plus 7 is 10. So that is fairly simple. v minus w is a vector -3, -4. -1 minus 2 is -3. 3 minus 7 is -4. And note 22 is an illustration. It is it's a picture. It's the geometrical interpretation of vector addition. And so study that note for a couple of minutes before you go on to the next example, which will be example 23. And so you might want to pause the video and just look at your notes for a minute. Assuming you've done that, let's go on to example 23. We have the vector 2, 3 and the vector 3, -1. And we've been asked to draw a few things in that picture. And this is the end result, and it looks very busy and very crowded, but I will break it down for you piece by piece. So the first thing we wanted to do is draw the vectors v and w. Now, the position vector representation of v is right here. The position vector representation of w is this one right here. But remember, vectors have length and they have direction, but they don't really have a position associated with them. So we can take our vector v and we can put it someplace else, and we do. We put another vector v right here, and we have a second vector w right here. Now, we take our initial position representation of v, and then we take our other representation of w, and we put these head to tail. Here's v, here's w. So v plus w is this vector right here. This is v plus w. Now, one of the nice things about vector addition is it's commutative, because normal addition is commutative. The regular addition in the real line is commutative. So w plus v is also v plus w. So we start with the initial position representation of w, and we add v, and we have v plus w. We've illustrated as w plus v, but it's the same vector. v minus w, I'm cheating a little bit here. I haven't talked about scalar multiples yet, but this is the vector -w. Well, right here's the vector w. What does -w look like compared to w? It's the exact same length of w, but in the opposite direction. So this is, we take our vector w, turn it the other way, we go in the exact opposite direction. That's -w. And so here's v plus -w, or v minus w, and that's this vector right here, v minus w. Now, in the number line, a minus b and b minus a aren't the same number. And so v minus w and w minus v aren't going to be the same vector either. So this is the vector representation of v minus w. It is not the representation of w minus v. And as you would guess, w minus v is the vector of the same length in the opposite direction.